To start the class soon. Okay, a few of students have not filled out the form. Please fill out the attendance now. Okay, there are 3 students haven't filled up. Okay, I will continue our lecture about Lood-Elmos inverter. Okay, to help you to recall back what are the Lood-Elmos inverter. Okay, you see from the slide. Okay, there are 2 figure here. One is enhancement Lood-Elmos inverter, another is depletion Lood-Elmos inverter. Okay, so these 2 Lood-Elmos inverter, the load here are the transistor. Okay, this is NMOS transistor. Okay, last week I have discussed about the advantage and disadvantage of both of these Lood-Elmos inverter. Okay, so there is a table that compare their disadvantages and advantages. Okay, I will further mention and discuss about the design of depletion Lood-Elmos inverter. Okay, this depletion Lood-Elmos inverter is evaluated, okay, to perform with better performance if compared to this enhancement Lood-Elmos inverter. Okay, why is that? Because one of the reason is the driver to the load ratio, okay, can be adjusted. Okay, and with these parameters that can be adjusted, the area they occupied by this inverter is also smaller. Okay, and then for NMOS load and for enhancement Lood-Elmos inverter, okay, the disadvantages here is one of it is the use of the 2 supply voltage. Okay. Okay, so I will go to this VTC of depletion Lood-Elmos inverter. Okay, this inverter, you see that the VTC look like this. Okay, it is also similar with the one that you have learned before. Okay, about the resistive load inverter circuit, the VTC is also similar. Okay, this is the VTC curve. Also plot with VOH, VOL, VIL, VIH. Okay, you see that here the VIL, this is input law. Okay, it is actually indicate the point of the slope. Okay, the point of the slope here. Okay, and then VIH also the point at the slope here. Okay, where there is a change at the output. Okay, and then for this inverter, there are also 3 operating mode. Okay, this 3 operating mode is the driver operating mode. Okay, they are driver operating mode and then load operating mode. Okay, the structure here, okay, which one is a driver? If you see the figure, okay, this one is a driver. This is the driver transistor. Okay, this is load. Okay, so here the driver will start to operate when the input is increased. Okay, and then the load transistor here, it will change the operating mode. Okay, so now I refer back to the table. Okay, you see that, okay, in this table, when the input is output low, means the input is low, the values is equivalent to output low. Okay, so the driver operating region or the operating mode is cut off. Okay, and then the load operating region, it is linear. Okay, and then output of course is high. Okay, and then if the input voltage is increased slightly to VIL, okay, this is also a low input voltage, but it is above the threshold voltage. VIL is above the threshold voltage. Then the driver start to become saturation. Okay, mean it start to conduct some current. Okay, but then the current is not increased. Okay, it is at the saturated, okay, condition. Okay, and then this when this driver is in saturation, the load operating region is also in linear. Okay, and then when the input is increased to input high voltage, then now the driver will operate in linear. Okay, and then the load operating regions will be in saturated. Okay, and the output here is small. Okay, when the input it become high, okay, and the value is as high as VOH, then the driver also in linear operation. Okay, and then the load is in saturation. Okay, the output here is also small. Okay, output small, this output is equivalent to VOL. Okay, this one you will have to remember the operating mode of the driver and load. Okay, okay, for this depletions load and MOS inverter, there are also some of the formula that can be used to calculate the critical voltages. Okay, here this is the first one about the calculations of VOH. Okay, these calculations, as you see, uh, this is about VOH. Okay, if we know that VOH, the output are high voltage, um, it means that there is no calculations. Okay, we straight away we can know that it is VDD. Okay, this one mentioned before, just like the resistive load and MOS inverter, the output high, when the output is high, then the values can be the VDD. Okay, and then that also means that the transistor, the driver transistor is in linear mode. Okay, so here this is the description. The input is smaller than the driver threshold voltage. Okay, this is for when, okay, this is for when the input is smaller than VTO. Okay, transistor is turned off. Okay, okay, sorry, this linear region just now I mentioned is driver transistor, right? This is not correct. This linear region is the load transistor. Okay, this is the load transistor is in linear region. Okay, and then the driver transistor is cut off. Okay, and does not conduct any drain current. Consequently, the load device which operate in the linear region also has zero drain current. Okay, so here the ID given for load is equals to 0. Okay, okay, and then also there is drain current for the driver is also 0 because here mentions that does not conduct any drain current. Okay, so next is about the calculations of VOL. Okay, so in this calculation, okay, the formula is derived. Okay, the formula is derived. So this is the formula. Okay, this formula we can use it to calculate the VOL. Okay, the derivations here does not show here. Okay, but how it is being derived, it is actually originated from this formula, 5.37. Okay, this one is quite similar to the derivation method in the resistive load inverter. Okay, but I will not further explain to you on these derivations, but what you need to know is this is the formula, and then the difference in the formula. Okay, for this depletion load NMOS inverter with resistive load inverter is that this formula, there is no resistive load, means there is no RL. Okay, this is how you should differentiate the formula. Okay, in this formula, there is no resistor value, no RL. Okay, and then this formula, there is a K load over K driver. You see the term here. Okay, this term we call it as the load to driver ratio. Okay, this one sometimes it is written as KR. Okay, this KR will determine the shape of the VTC. Okay, so others like VOH, VTO, this is also in the calculations. Okay, we need to define the value to substitute into this formula to get the VOL. Okay, so for this VOL, since this is output loss, right? Okay, so the input, okay, input must be high. Okay, input voltage must be equals to VOH or VDD. Okay, so in this case, the driver transistor operate in linear region. Okay, and then the depletion type load is in saturation. Okay, so this is how you should understand. Okay, and now I goes to the calculations of VIL. Okay, this is about the calculations of input low voltage. Okay, so for this one, this we need to take into account of the slope. Okay, why I say that because in the derivations they are dV out, dV in. Okay, but in this formula, this is the final formula. Okay, this is the final formula without the dV out over dV in, because it is being substituted with -1. Okay, remember the -1 indicate the slope, the point at which the slope change. Okay, just this is a dV out over dV in. Okay, so V in is equals to input law. Okay, when it is equals to input law, then the driver transistor operate in saturation, while the load transistor operate in linear region. Okay, and then the derivations of the formula is shown here. Okay, in equations 5.39 and 5.40. Okay, using the Kirchhoff current law. Okay, again, this is current. Okay, this current is maybe this the load current. Okay, so it's also similar. method of derivations. This one you don't need to remember. Roughly you know that will be enough. Okay. So after all the derivations, so this is the ones that you should get. Okay, with VTO plus the load over the driver ratio. Okay, multiply with V out minus VDD plus VT multiply with the V out. Okay, this is the absolute values. Okay, so this formula, okay, the formula that I show here, okay, this one you no need to memorize. Okay, you no need to memorize because some will give you. Okay, some of the formula will give, but the problem is which one to use. You will have to learn. Okay, you will have to learn and remember. Okay, and the last one is about the calculations of VIH. Okay, so VIH is the largest of the two voltage point on the VTC at which the slope is equals to -1. Okay, this is another slope at VIH. Okay, since the output voltage corresponding to this operating mode is relatively small, the driver transistor is in the linear region, and the load transistor is in saturation. Okay, again, this is the derivation. Okay, by differentiating this formula, then to get this formula. Okay, after that, this formula need to be arranged to get the VIH equals to VTO plus 2 multiply V out plus the load to the driver ratios multiply with minus VT multiply with V out plus the differential of VT over DVO. Okay, let me see. Okay, looks to me this is not the final one because this term will need to substitute with this. Okay. Okay, so this is the calculation that need to be used, the formula, okay, that need to be used for calculations. Okay, in depletion load inverter, okay, there are some of the parameters here that can be used to design. Okay, the design here is about the design of depletion load inverter. Okay, and then how to design this inverter is we design it based on the VTC. Okay, the DC characteristic of the inverter, we can actually change, okay, and redesign. Okay, and then how to design it? We can use this parameter, voltage supply, okay, VDD, the threshold voltages of the driver, and the load transistors, the width over length ratios of the driver, and the load transistors. Okay, so these are the parameters that we can use to design the inverter with a better performance. Okay, for example, okay, like power supply. Okay, power supply voltage VDD. We cannot simply choose a value. We cannot choose a very high VDD. Okay, like maybe 15 volt. Okay, 15 volt is considered high. Okay, so we cannot simply use why? Because this will cause high power depletion, high power dissipations. Okay, high, not recommend. Okay, why? Because it will cause high DC power dissipation. Okay, so you see most of the inverter, the range of the VDD that they will use is between 2 to 5 volt. Okay, this will get a low power dissipation. Okay, so this one you must understand the concept behind. Okay, so VDD is important, And then threshold voltage of the driver and the load transistor. Okay, this is about VTO. Okay, this VTO determines at which level the driver and load will start to operate. Okay, so below the threshold voltage, the driver will be in cutoff. If above the threshold voltage, then the driver will start to operate. Okay, if we want to make the driver to start operate, okay, we need to set a suitable threshold voltage. Okay, how do we set? Okay, we cannot set it ourselves actually. Okay, usually threshold voltage, they are set by the fabrication process. Okay, the material that is used during the fabrication process. And then the value, about the values. Okay, the values can be small or high. Okay, large, small or large value. Okay, so between small and large value, which one is better? Okay, threshold voltage. Okay, if we want to set it to small threshold voltage, okay, there will be another effect. Okay, the effect here, what I want to say is the drawback. Okay, the negative effect. Okay, if small threshold voltage, then it will cause significant static power consumption or power dissipation. Okay, this one I will mention. Power dissipations, there are many types, static and dynamic. Okay, so static is another type of power consumptions. So this static power consumptions means that is the power this power consumptions that occur when the transistor is not switched. Okay, so static means is in static. Okay, not moving and not switching. Okay, so small threshold voltage will cause significant static power dissipation. We also cause small noise margin. Okay, so we cannot set the threshold voltage too small. Okay, we must set it with relatively a larger value. Okay, but how do we set it is to determine what is the materials that need to be used when we do the fabrications. Okay, and then the next one is the width over length ratio. Okay, width over length ratios of the driver and the load transistor. Okay. Okay, so here there are some of the descriptions here. Okay, it is about the driver to load ratio and then the critical voltages. Okay, critical voltages point. Okay, the general shape of the inverter VTC and ultimately the noise margin are determined essentially by the threshold voltage of the driver. Okay, and then the load devices. Okay, so this is the one that I mentioned just now. Okay, we need to make sure that the noise margin is high. Okay, small noise margin means that the circuit cannot sustain or cannot is not good to it's not immune to the noise. Okay, we need to make sure that the noise margin is high noise margin. Okay, so threshold voltage will determines the shape of the VTC and then the noise margin. Okay, and okay, and also this noise margin and the shape are determined by the driver to load ratio, K drive over K load. Since the threshold voltages are usually set by the fabrication process, The driver to load ratios emerge as a primary design parameter, which can be adjusted to achieve the desired VTC shape. Notice that with K prime and driver equals to K prime load, the driver to load ratio is solely determined by the width over length ratio of the driver and the load transistor, okay, by the device geometry. Okay, when we consider the width over length ratio, it is meant by the device geometry. Okay, and figure 5.14 shows the VTC of depletion load inverter circuit with different driver to load ratios. KR equals to K driver divided by K load. One important observation is that unlike in the enhancement load inverter case, a shape VTC transitions and larger noise margin can be obtained with relatively small driver to load ratio. Okay, thus the total area occupied by a depletion load inverter circuit with an acceptable circuit performance is expected to be much smaller than the area occupied by a comparable resistive load or enhancement load inverter. Okay, so by the statements here, okay, the driver to load ratio, okay, it determines the noise margin and the VTC. Okay, so when it is small, then it will give a shape. This is not shape, this is sharp. Okay, will give a sharp VTC and also a larger noise margin. Okay, and then the total area. Okay, the total area occupied will also be smaller. Okay, because of this small driver to load ratio. Okay, and then this area occupied by this depletion load inverter is smaller than the resistive load, and then the enhancement load inverter. Okay, and this one is the VTC of the depletion load inverter. Okay, the shape here you see that there are three shapes. Okay, these three shapes are stimulated. Okay, based on different driver to load ratio. Okay, this is K driver over K load. Okay, so different ratios will give different shape of the VTC, especially the difference here. The difference here is on the slope here. Okay, it change based on the ratio. Okay, the power supply voltage VDD determines the levels of the output high voltage VOH, since VOH equals to VDD. The output low voltage VOL is usually the most significant design constraint. Designing the inverter to achieve a certain VOL value will automatically set the other two critical voltages, VIL and VIH as well. Equations 5.37 can be rearranged to calculate the driver to load ratio that achieve a target VOL value, assuming that the power supply voltage and the threshold voltage value are set previously by independent design and processing constraint. Okay, this one 5.37 is referred to this formula. Okay, this is the formula. Okay, so with the formula just now, 5.37. Okay, this is the formula from equation 5.37. And then this equation can be rearranged to get the KR. Okay, in these equations there is a K drive and also K load. Okay, so we rearrange it, then we can get this. Okay, this formula. Okay, with the VT multiply with the VOL square divide by 2 multiply V out minus VTO multiply VOL minus VOL square. Okay, and then the driver, okay, the driver to load ratios is also given as this KR. Okay, KR is equals to K prime. Okay, this is mean that, okay, this K prime driver multiply W over L. Okay, this is the K driver divided by K load. Okay, I mentioned this before. K equals to K prime multiply V over L. So this is the one, okay, that represent the K, okay, for driver and load. Okay, since the channel's doping density and consequently the channel's electrons mobilities of the enhancement type driver transistor and the depletion type load transistor are not equal, we shall expect that K driver is not equals to the K load. Okay, this is not K, okay, this is K prime. Okay, you see this one. So just now I mentioned it as K, it should be K prime. Okay, there is a prime here. Okay, K prime driver and K prime load. Okay, only if K prime driver is equals to K prime load, can the driver to load ratios be reduced to W over L? This is the width over length of the driver and width over length of the load. Okay, so this one you can understand. Okay, because if based on this one, the formula, if these two values are equal, then it left only the width over length for both driver and load. Okay, which is equations 5.48. Okay, finally, note that the design procedure summarized above determine the ratios of the driver and the load transconductance, but not the specific width over length ratios of each transistor. As a result, one can propose a numbers of design with different width over length ratios for the driver and for the load device, each of which satisfy the driver to load ratios conditions stated above. Okay, actual sizes of the driver and the load transistor are usually determined by other design constraints, such as the driver, this is current drive, okay, capability, okay, current drive capability, and the steady state power dissipations and the transient switching speed. Okay, so this is another parameter, okay, and constraint, okay, that will determine the size of the driver and the load transistors. Okay, so this is about the design of this depletion load NMOS inverter. Okay, and furthermore, okay, there is about this power and area consideration. Okay, so when we design the inverter, okay, our considerations is actually on the power and area considerations. Okay, the steady state DC power consumptions of the depletion load inverter circuit can be easily found by calculating the amounts of current being drawn from the power supply during the input low state and input high state. When the input voltage is low, when the driver transistor is cut off, V out is equals to VOH. There is no significant current flow through the driver and the load transistor. Okay, consequently, the inverter does not dissipate the DC power under this condition. Okay, when the input is at the high state, with input is equals to VDD and the Vout is equals to VOL, both the driver and load transistor conduct a significant current given by ID, this is the drain current, okay, is equals to K load divided by 2 multiply with minus VT multiply with VOL square. Okay, so these equations also can be written as this way, okay, with K driver over 2 multiply with 2 multiply with VOH minus VTO multiply VOL minus VOL square. Okay, so here you see that the drain current for the inverter is this one. Okay, this is the formula. So if we want to calculate the drain current for the depletion load and MOS inverter, this is the formula that we should use. Okay. Okay, assuming that the input voltage level is low during 50% of the operations time and high during the another 50%. The overall average DC power dissipations of this circuit can be estimated as follows. Okay, so this is the formulas to calculate the average DC power dissipations. Okay, the formula here is with VDD divided by 2, multiply with K load over 2, multiply with minus VT load, multiply with VOL square. Okay, so this one we also can rewrite it with VDD divided by 2, multiply K load divided by 2 and multiply with this. Okay, so if the VTO is given, okay, and VOH is given, then we can use this as well. Okay, so remember that drain current only occur when the driver is in linear mode. Okay, means the input is high. Okay, so when there is a drain current, then then we can when there is a drain current means that there is a power dissipation. Okay, power dissipations we can determine it using this formula 5.50. Okay, so as a summary, these are the formula. Okay, that is for the depletion load and MOS inverter. Okay, so this is for you to have an overview of all the formula for all the critical voltages. Okay, so this is the end for this depletion load inverter. Okay, next I will mention about CMOS inverter. Okay, this is another type of inverter. Okay, I see that we still have time. Maybe I will cover that. Okay, before I continue to the next topic, do you have any questions? Okay, if no questions, then I will go to the next one. Okay, this is about a CMOS inverter. Okay, in part 3. Okay, part 3 under chapter 5. Okay, is about CMOS inverter. Okay, this CMOS inverter will be compared with the another three types of the NMOS load inverter. Okay. Okay, similarly, for CMOS inverter, I will also cover on the calculations and then the VTC. Okay, it is not quite difficult. Okay, if you can understand what I have mentioned previously, then for CMOS inverter, you also can get it. Okay, especially on the calculation side. Okay, CMOS inverters has two important advantages over the other inverter configurations. The two advantages of CMOS are the steady state power dissipations of the CMOS inverter circuit is virtually negligible, except for small power dissipations due to linkage current. In other inverter structures, a non-zero steady-state current is drawn from the power source when the driver transistor is turned on, which result in a significant DC power consumptions. The voltage transfer characteristic VTC exhibits a full output voltage swing between 0 volt and VDD, and that the VTC transition is usually very sharp. Thus, the VTC of the CMOS inverter resembles that. Okay, let me see who raised up their hand. Yes. Oh, okay. Sorry. Okay, I should share my screen. I didn't share my screen. Okay. Okay, sorry about that. Okay, so this is a slide that I mentioned just now. Okay. Okay, this is about the advantages of CMOS inverter. Okay. The two advantages here. Okay, I repeat again. Okay, the steady state power dissipations of the CMOS inverter circuit is virtually negligible except for small power dissipations due to linkage current. Okay, in all inverter structures, okay, a non-zero steady state current. Okay, I'm sorry, here quite sensitive. Okay, I accidentally press. Okay, so a non-zero steady state current is drawn from the power source when the driver transistor is turned on, which result in a significant DC power consumption. Okay, this is about power dissipations. Okay, the power dissipations in CMOS is smaller. Okay, if compared with other inverter structure. Okay, and if in the same case, if the power supply is high, okay, of course, this CMOS inverter will dissipate significant DC power consumptions. Okay, and another advantages is on the VTC. Okay, CMOS inverter has exhibit a full output voltage swing between 0 volt and VDD, and that the VTC transitions is usually very sharp. Okay, thus the VTC of the CMOS inverter resembles that of an ideal inverter. Okay, VTC of the inverter, we want to get it as sharp as possible, which is near to the shape of an ideal inverter. Okay, so you see a lot of VTC, the shape, okay, of the inverter, it is not very sharp. Okay, the transition is not very sharp. Okay, it means that is not the ideal one. Okay, but the realistic one. Okay, the most the the good one, okay, what I want to say is the good one is the one that you should get with the sharp transition. Okay, so CMOS inverter, all of you know, okay, it is like this, and then with PMOS and NMOS. Okay, for this one, this is PMOS. Okay, but this one, you see the symbol here, the drawing. Okay, the drawing, this is actually looks like NMOS, but actually this is PMOS. Okay, please take note. Okay, you need to know. Okay, CMOS means use PMOS and NMOS. Okay, previously one is only NMOS. Okay, so this one I think I no need to mention because you know. Okay, since NMOS and PMOS transistor must be fabricated on the same chip side by side, the CMOS process is more complex than the standard NMOS only process. In particular, the CMOS process must provide an N-type substrate for the PMOS transistor and a P-type substrate for the NMOS transistors. The substrate of the NMOS transistor is connected to the ground, while the substrate of the PMOS transistor is connected to the power supply voltage VDD in order to reverse bias the source and drain junctions. Okay, this is about DC characteristic CMOS inverter. Okay, let me see this one. I think I'm going to cover in the next class. I feel like to cover next class because I see that now only have 10 minutes and then later we will have tutorial. Okay, I need to have some times to go to another venue. Okay, seems I don't have time to cover the next few slides on DC characteristic. Okay, so I think I will just stop here. Okay, just now is about the introductions of CMOS inverter. I will talk about this next in the next class on Wednesday. Okay, so I stop here. Okay, let me check your attendance. Okay, we should get a 25 form. Okay, okay, I have all your forms. Okay, I want to check with 4 of you. Any one of you sign in the Google Meet? No. Okay. Okay, I have 29. Just now I saw total is 29. Suppose there's only 26. Okay. The forms that I get is 25, means one more. Okay. I see one student just now join. Okay. And then I'm not sure who is the one that haven't filled up the form. Okay, but it's okay. Maybe I'll check later. I cannot check. I cannot check now because I don't have much time. Yeah, I'm okay. Minus, okay, just now 29, right? Minus 3. Minus 3 is 26. Okay, initially it's 28. 28 minus me is 2, and then Yan Chan minus 1. Yan Chan still have to. Hmm? Oh, okay. You see, just now he come in. He logged out.
Before he come in this class,
Uh-huh.
he with Google Class. When he entered this room, he clicked the Google.
Okay, but just now why I see the number is 29. You still sign in. Oh, okay. So I exclude you 25. Okay, correct. Yeah. Okay, no problem already. So we can dismiss class now. Mm. Students who have a tutorial later, please stay back. Okay. I will join you later. Okay. I need to exit from this meet. Okay. Later I will rejoin for the tutorial class. Okay. Thank you.